So I'll teach this topic for several days, maybe 2 or 3. So first, I'll explain aggregate analysis, and then accounting method, and potential method, and dynamic table. First, aggregate method analysis. First, let me explain the example of stack operation. There are 2 stack operations, push of x and pop. So push and pop run in constant time. So push of x puts, we assume, a stack, and there are some items in the stack, and we perform push of x, then put x on the top of the stack. And when we perform pop, then we remove the top item from the stack, only one item. So push and pop run in big O of 1 time, and thus the cost of each is 1. And the actual running time for n operations is theta of n. So since one operation takes big O of 1 time, m operations takes theta of n time, and we will define this as a cost. So let me introduce a new operation, multipop. So multipop of k removes k items from the stack. So you look at this pseudocode, multipop of s, k. So s is the stack name. We remove k items from the stack. So we repeat pop of x operation from the stack. But if the stack is empty, we stop this. So okay, there is an example here. So this is a stack with 6 items. So first, let's perform multipop of s, 2. Then we remove 2 items from the stack like this, and then our top pointer points to the top item. And so the cost is 2 because we popped 2 items. But look at this, multipop 6 items. But in this case, there are only 4 items. So the cost is not 6, it's 4. So the cost is the minimum of k and the number of items in the stack. Okay. Now let's analyze n operations where they are consist of push, pop, and multipop operations. And initially the stack is empty. An intuitive analysis of the time complexity is this, big O of n squared. Why? There are n operations, and we know that the worst case cost of one multipop is big O of n. So it is this. The stack is filled with n items, and then we run multipop n. Then it takes big O of n time. So, and if all operations are multipops, then it takes big O of n squared time. But this scenario is infeasible because it is impossible to run each multipop operations with big O of n time. So this cost isn't tight. So let's use aggregate analysis to achieve big O of n running time. We know that stack is initially empty, and we perform n push, pop, and multipop operations. So let's enumerate the sequence of operations. Then push, push, pop, push, push, pop, push, push, multipop, and something like this. Then first, let's convert multipop operations into pop operations. So in this case, we can pop 2 items, so it is converted to double pop operations. But assume that the next multipop operation is multipop 10. Then what is the real number of pop operations? Let's see, push, first it's push, and next push, and pop, and push, 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 and pop, 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 pop. So even though the next multipop operation is multipop of 10 items, there are only 2 items in the stack. So it is converted to 2 pop operations. Okay. So in this converted sequence, the number of push operations should be bigger than the number of pop operations, because pop operation is possible only if there is a push operation. So this is important. The number of pop operations is smaller than the number of push operations. And the number of push operations is smaller than n, where n is the total number of operations, which are push, pop, and multipop. So this is an important inequality. We know that in this converted operation sequence, the number of push is smaller than n, and the number of pop is smaller than n. So the number of push and pop operations is smaller than 2n. So, and the total cost, since each push or pop operation takes constant time, the total cost is big O of n. Look at this. There is no multipop in the converted operations. So it is big O of n. And now let me introduce the amortized cost. The amortized cost is a virtual cost that is the total number of costs over the number of operations. So it is big O of 1. It is an average cost of each operation. But it is guaranteed that the n operation takes big O of n time. Any questions? Okay, let me move on to another example. This is incrementing binary counter. And consider the problem of implementing a k-bit binary counter that counts upward from 0. We use an array of k entries from A0, A1 through AK minus 1. And let's define the cost of increment operation be proportional to the number of bits flipped. For example, the increment A is done like this. So let me show you this. Let me show you this example here. First, initially it is 0, so they are all zeros. And assume that we have the k is 5-bit counter. Then, if we increment this, it becomes this one, 1. And then, if we increment this, it becomes this one, and then this one. So this is the process of incrementation. Then look at this. Let me explain the pseudocode for incrementation. If we increment this, we convert 1 to 0, 1 to 0, and if we mid 0, then it converted to 1. So this is the pseudocode. If the last from the right bit is 0, it is converted to 1. That's all. But if there are some 1s at the end, they are converted to zeros like this. And then the first 0 we come across is converted to 1. Now it is explained here. Initially, the index bit I is 0. So if I is a.length, that is k, and ai is 1, ai is converted to 0, and I is incremented. So this while loop converts all tailing ones into zeros, and then if it comes across 0, it exits the while loop. And then it sets the ith bit to 1 if I is smaller than k. It means that if all bits are 1s, then we convert it to 0, 0, 0, 0, 0, and there is nothing here. So this counter is a wraparound counter. Okay, the main cost of incrementation is, assume that the main cost is these two lines, the bit flip. And let's calculate the cost and total cost. Initially, it is 0, and then it is converted to 1, and only one bit is flipped, so the cost is 1. And next, from 1 to 2, 2 bits are flipped. The cost is 2 in this incrementation, so the total is 3. 1 plus 2 is 3. And next, from 2 to 3, only one bit is flipped, so the cost is 1. The total is 3 plus 1 is 4. And this time, 3 bits are flipped, so the cost is 3, and the total is 7. Okay, then let's estimate the cost of this binary counter incrementation. A single execution of increment takes theta of k time in the worst case. For example, this one, all ones are converted to zeros, so the cost is k. So a sequence of n increment operations may take big O of nk time in the worst case. So each the number of operations is theta of n, and the incrementation is in the worst case theta of k, so it is big O of k. So if we multiply these, then they are big O of nk in the worst case. But we can do better. We can show that big O of n operations takes only big O of n cost. Let me show you how. Let's analyze this by not by row, but by column. So look at this. The bit A0 is flipped in every increment operation, 1 0 1 0 1 0 like this. So if we perform n increment operations, then A0 bit is flipped n times, and then bit A1. So it is flipped in every other operation. So the number flip is n over 2. And A2, actually they are 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So the bit A2 is flipped at every fourth operation. So it is n over 4. And similarly, it is n over 8. So we have to calculate this from the summation of n over 2 to the I, where I is from 0 to k minus 1. So we have to add n over 16 like this. So this is smaller than the infinite series, and it is since the common factor is 1/2, it is this. That is 2n. So the total cost is big O of n for n operations. for any n operations more exactly. So the amortized cost is the total cost over the number of operations, which is big O of n. Okay, I explained aggregate analysis on these two examples. They are a step with multi-pop operation and incrementing binary counter. Okay, then let me move on to accounting method. So accounting method is a tool of analysis. So we will show that by some guess, it is we can simplify the amortized analysis. We want to show that in the worst case, the average cost per operation is small by analyzing with amortized cost. So let CFI denote the actual cost of the ith operation. So this is actual, and Ci hat is amortized cost of the ith operation. So we want to show that the summation of all amortized operation is bigger than the summation of all actual operations. Then this can be an upper bound of this. To show this, we will show that this is positive for every n. And this is called the credit. Okay? So let's get back to the example of step operation. So actually, the cost of the operations are 1 for push, 1 for pop, and min ks for multi-pop k. S is where S is the number of items in the step. Okay. So let's assume that the amortized cost of the operations are this: 2 for push, 0s for pop and multi-pop of k. Then what is the cost of n operations for any n operations? Because the maximum is 2, it is 2n, so it is big O of n. So the amortized cost for any n operations is big O of n. So if we can show that the summation of amortized operations is bigger than the summation of actual operations, then the cost of n actual operations is also big O of n. So to show that the summation of the amortized cost is bigger than the summation of actual cost is to show that this is 0 or more always, which is called the credit. Okay, so to explain this, I will show an example. So look at this. One item is pushed here. Then since the amortized cost for push is 2 and the actual cost for push is 1, the summation of amortized cost minus the summation of actual cost is 1, since this is 2 and this is 1. So the credit is 1. Okay, next, 2 items are pushed. So the amortized cost is 2 plus 2, which is 4. And the actual cost is 1 plus 1, which is 2. So 4 minus 2 is 2. So the credit is 2. So let's ignore this. And then 3 pushes. The amortized cost is 6. And the actual cost is 3. So it's 3. So the credit is 3. So until now, the credit is always 0 or positive. And pop. Look at this. There are 3 pushes and 1 pop. So the amortized cost is 6. Since push cost is 0, pop cost is 0. The amortized, the summation of the amortized cost is 6. And then the actual cost is 4. So it is 4. So the credit is 2. So it is still positive. And next, push. Then 4 pushes and 1 pop. So the amortized cost is 8 and the actual cost is 5. So the credit is 3. Still positive. So we can get some idea that the credit is always 0 or positive. But I didn't show all cases. But we should prove that the credit is always 0 or positive at any case. N pushes plus n pops. Then the actual cost is, the amortized cost is 2n. The actual cost is n plus m. So it is n minus m. So if n is bigger than or equal to m, it is always 0 or more. Why n is bigger than or equal to m? Because as we observe here, at any time, the number of pop operations performed cannot exceed the number of push operations performed. So the amount of credit is always non-negative. So the total amortized cost is big O of n, and since credit is always 0 or more, the total actual cost is big O of n. Any questions? So actually, this analysis is similar to, the result is similar to the aggregate analysis, but the calculation is easier. So actually, the amortized cost is not calculated. It is guessed like this. This is our guess. and then show that the credit is always 0 or positive. And next, let me explain the example of incrementing binary counter. In this case, the actual cost for bit set is 1 and bit reset is 1. But let's assume that the amortized cost for bit set is 2 and bit reset is 0. So let's get back to the static example. In this case, the push cost, the actual cost for push and pop are all 1s. But in this case, the cost for pop is 0 and the cost for push is 2. So actually, the pop cost is prepaid by push. So that's the main idea of this amortized analysis. And similar idea is applied to this case. The bit reset cost is prepaid by the bit set cost, since we can reset a bit if and only if the bit is set. This idea is similar to the idea that the pop can be performed if and only if the push is performed in advance. Okay, let's look at this. First, from 0 to 1, and then only the last bit is set. So the amortized cost is 2. So the summation of the amortized cost is 2, and the summation of the actual cost is 1. So the credit is 1. So it is positive. And next, 1 bit is set and 1 bit is reset. So the amortized cost is 2. So the cost for set, and the actual cost is also 2. 1 for set and 1 for reset. So it is 0. So the credit is bigger than or equal to 0. And next, okay, so it was in the middle of the state. Now, here, this is the middle of the process from incrementing from 1 to 2. Then this bit should be set to 1. So now 2 sets, which is 4. The amortized cost is, the summation of the amortized cost is 4, and the summation of the actual cost is 3. Set, reset, set. So the credit is 1. So 0 or positive. And next, incrementing 2, and only 1 bit is set. So it is 1, 2, 3. 3 sets, 6. 3 sets and 1 reset. So 4. So the credit is 2. It is 0 or more. And next, let's look at this state. 1 set, 2 sets, 3 sets, and 4 sets. So the amortized cost is 8, and the summation of actual cost, we can calculate it by the aggregate way. 4, 2, 1, 7. It is 1, so it is 0 more. Similarly, one can show that the summation of amortized cost is bigger than the summation of actual cost. So let's get back to this. And it is true because bit reset operation is possible. The number of total bit reset cannot exceed the number of bit set. Okay, so the amortized cost is twice the number of bit set, and the actual cost is the number of bit set plus the number of reset. If we subtract this from this, then the number of set is minus the number of reset, and it is 0 or more. Okay, then this explains that the summation of the amortized cost is bigger than or equal to the number of actual costs. It means the summation of C hat is bigger than or equal to the summation of C. And then since the summation of C hat is 2n, the summation of the actual cost C is at most 2n, which means this is big O of n. So the summation of all actual costs is big O of n.